Hi, everybody. My name is Marco Pritoni. I'm a scientist here at Lawrence Berkeley Lab. I work with Marianne and others. My area of expertise are controls and analytics for buildings, and more like grid building interaction. Quick questions to you guys. Who knows about or teaches HVAC here? Maybe 50%. Who teaches building automation systems? Okay. Maybe. And who actually knows how to program or code in any? Okay. Sounds good. So I know you guys already saw yesterday a couple of presentations on building automation systems and the kind of the overlook for the future. This is my perspective, so don't take it as completely universal or true. I hope this is high level enough for people who have never heard of it, and there's a bunch of interesting things for experts. So a building automation system, or BAS, is a computerized intelligent network of electronic devices designed to monitor and control HVAC lighting and other systems in a building. So this is the picture of a smart building, what we call now smart buildings. And there's different uses. There's definitely HVAC, there's lighting. What is this? Security. What is this? Security again, I don't know. But maybe entrance, like there's network stuff, there's water. But it's kind of funny that in most of the cases, what you actually find in a building looks more like this. And I see nods from other people. This definition, this is like Siemens 2018. No offense to Siemens, but this is like something from the 2000 something, 1995, Windows 1995, glorious here, and a rooftop unit that has been there for about 40 years. This definition is actually in the BACnet protocol, which is from 1995. So when they were thinking about that, they were probably thinking about smart buildings, but they were seeing this, which is kind of sad. This is a quick timeline of what happens. It's a subset of all the events in the BAS history. You got the first thermostat in 1883 by the guy who funded Johnson Controls. You got the first air conditioner by Carrier in 1902 when he was trying to dry a facility that was producing paper. And then you got nothing for other 60 years, where people finally decided that I have to manage this huge HVAC, these fans and other things. And the only thing they had at that time, it was like super exciting to design a building only with pneumatics. This was running big industrial facilities, and now you have things like this. Look awesome. And yeah, they're still there, some of there. So you have an air tank there, you have different valves, and you have pressurized air that moves things. You obviously need to calibrate this every 5 minutes, otherwise the temperature goes plus minus 50. The control sequences are whatever the hardware says. You'll never think of changing anything because it's just too scary. Exciting time to be there because that was the only option. Forward 10, 20 years, we got the first electronic devices, so that's great. Now we have wires and things that we can connect. That's great. Now you have thermostats, you have relays, you have timers. You can buy this on Amazon after 30 years. A lot of wires going around. I have, things here that Chris gave it to me. A first temperature logger of that time, where if you log more than 1 day, it overrides it. So that's awesome. The temperature control is tighter. You can get by with less calibration. Easier to modify control sequences. It's like click. That's the control sequence you can modify. Still fairly exciting time. My dad was a technician in the emerging electronic industry back in the 70s in Italy. And he used to have all these drawings and say, oh, if you connect this to that, and now it's like a chip that does, is 1 year work in one chip. Things got even more exciting during the 80s where, the microcontrollers were available. So a microcontroller is something like this, which I'll go into details later. The whole system allows you to have a more compact and, going back, this is a mess. This is less messy. But basically, you have more accurate control of temperature. You can actually program these things to do different things as opposed to actually to have to rewire things. It's easier to access information. You have the wonderful graphics. You can even get graphics out of this box. You can trend things without the metallic piece of paper, and you have alarms. So to be clear, in the 80s, Pneumatic didn't disappear. It was still there. So this is a fairly qualitative way of how the market went. So this is building automation from the beginning of the century, last century, to 2001, when it was like an old graph, where pneumatics went up, and then around the 80s went down, and other systems like electronic and electric systems went up, and then direct digital control, which is what we just saw, went up and up. So in addition to this, which are the market sales, what happens in real buildings is that you don't change the system for 30 years, and so you still have 2 generations ago of things, and I see a lot of nods. And Chris knows how many crazy systems we have here, including large part of our campuses is run on a control system that went bankrupt in 2008 or 6 or something. And so it's running on a MS-DOS machine. A quarter of the campus is still running on MS-DOS. Right. Which is a pleasure. So the controller is a pretty neat tool. It has inputs and outputs, so it reads information. This is you probably are familiar with this. This is an air handling unit with fans and different dampers. And this guy reads all the inputs and writes different outputs to change the speed of the fan or change the status of different components. You can have control code running on this thing. So you can have schedules. You can have control sequences that says, if the temperature is lower than that, the outdoor temperature is lower than blah, 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 enthalpy, blah, 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 then change the speed of the fan. That was a very quick explanation of a control sequence. You have alarms. You can manage alarms. And you have external communication. And then we'll get to the architecture of this in a minute. But the communication of this device with a workstation allows you to visualize things and possibly to manage them remotely on multiple units. If you're lucky, you can get additional features which are data storage in the unit, so you can trend data inside the controller. You can have access to visualization directly. You may have some security features. If you're very lucky, this actually talks IP, and I know you guys saw a talk by Paul yesterday that was talking about the networking and IP devices. And the newest ones also have web services, which means you can interact with this with tools that are more advanced and more like IT-centered. Where does this thing live in the whole architecture? So you have the layer of the field devices that actually are connected to the HVAC and the other systems. You have field devices that control these things directly. Then you have another tier of controllers that control the controllers and manage the overall schedule, interlocks, alarms, and security. And then you have typically an enterprise level layer which has configuration, user interface, long-term storage of the data if you're trending, visualization, and additional features. So who's familiar with this? So who's been through this? How painful is this? It's pretty painful. One of the challenges that many people face, and here at the lab we have multiple building management systems in the same building. So you have half of the building as Johnson Controls, half is ALC. And so you can't see anything on the same computer. They don't talk to each other. It's a disaster. So this is the reason why in the 1990s they were like, well, this doesn't kind of make any sense. And if you go back to the graph that we have before of the market penetration, you have all these companies, Johnson, Siemens, Schneider, Crane, and the others who had their proprietary systems. And then at one point, this is an example. This is not 1990s, it's 2018, a military base we work with. They have 27 buildings, 27 BMS, 27 computers in a room. And so you have a guy who moves around on wheels, and it's like, what is that building doing? What is that building doing? Which is pretty funny, but kind of a disaster. So you have the two systems, they don't talk to each other, and there's really nothing you can do. Or there was nothing you could do in the 90s. Then people came kind of forward and said, well, this doesn't make any sense. We should adopt more and more standard protocols. So, and you can see the emergence of Modbus comes from the industrial world. Loanworks is a early semi-proprietary but open, meaning that if you have their chip, it works for everybody. And BACnet is an effort led by ASHRAE to find a protocol that could be used by multiple vendors. And so vendors moved slowly but steadily towards having using these different systems. And BACnet is now fairly popular, so you can buy one of those controllers that talks BACnet. The issues are not completely solved because, as you can see now, this guy has one computer with three things that all talk BACnet. But the reason why the problem is not solved is, one, as we said before, the life cycle of building automation systems is very long. So you got the same system for 30 years. People are even proud. My system from the, like your car, from the 70s is still there and still working. They're very expensive to replace, both because the hardware costs a lot, both because the software is very expensive, the licenses, and because replacing and rewiring things is very expensive. Then, what you got, like in Italy, you have different dialects and people don't understand each other. So in BACnet, what happened is it's kind of standard, but different manufacturers can have their own proprietary objects that you can't quite share with the others. And so it basically became mostly, the building is mostly interoperable with our system, but in theory. So you can't quite take one system and plug in another system and it kind of works. It takes days and days to actually set it up. The other issue that was clear from the beginning, if you look at the BACnet site, it tells you, but it's not clear maybe to people who bought this, is that protocols are not control languages, which means if two systems can talk to each other, but the program that runs them lives in a controller in a specific language. So if you have ALC and Johnson Controls, the ALC program, you can move that program into a Johnson Control program system that you buy because it's a different language. So even though they speak the same thing, the brain has unique mapping, a unique logic. And so, and we'll see some solution to this that came about later. The other issue that people know if you are more like in the IT and networking world is that BACnet is great, is better than nothing, but it's a special purpose network. It's monolithic. It's just this thing, blob. It's a unique thing, and it's not IP based. So it can run on IP, but it's not IP based. This is the picture of monolithic versus the internet. The internet architecture is what made it one of the reasons why it became very successful. It's you have a lot of protocols here at lower layer. You have a lot of application, your Netflix, your Google, your whatever, and IP in the middle. So if I want to swap something here, I can swap it. If I want to swap something here, I can swap it. While BACnet is just big things. So can you run a new application on BACnet? Sort of, but if you have another protocol, maybe that it doesn't communicate with that BACnet. So there's a lot of practical issues which are more in the IT universe that make this protocol workable, but not super, it doesn't look forward a lot. So since the problems were not solved, somebody came and proposed a truly open system. And this is my kind of funny way of saying truly open. I saw several pitches from people on YouTube watching. And the truly open system means you pay me money and you can talk to all the systems. So around 2000 something, somebody came out with a system which is called Tridium Niagara, which was then bought a few years later by Honeywell. And it's called the Niagara Framework. It's a Java framework. So the exciting thing is that these guys at least didn't reinvent the wheel and reinvent another language. They used Java, which is very popular programming language, to have a bunch of applications that deal with graphics, human interface with other systems and protocols, databases, other protocols underneath, and historian, alarming, and control. Everything is inside this Java virtual machine, which lives here. So that's great because then I can talk to any other devices and I can code my logic in this block here, and then like one ring, what's the Lord of the Ring quote? One ring to, yeah, something like that. So anyway, so the truly open means if you buy my system, which is not open source and it's not even free, you can deal with all the other systems. So that's sort of the market, how it was. Although it's very effective. So the JACE is what Marianne was mentioning before, the gateway. This is a single unit, which is more than a microcontroller. It's actually a microcomputer that has a lot of potential to do multiple things and can be upgraded easily. Now, how much actually changed after 2000? This is a zoom into my timeline that I had before. After we had BACnet, we were very excited about BACnet. Connectivity now, system on IP, control system on IP can talk to the internet. Great, awesome. Web services, Java, which is what we just saw. From then to now, there has been a few things. ZigBee, which is one of the examples of the wireless protocols. So ZigBee is important because it brought lighting into building automation system. But it's also important because people realize that a lot of cost in wiring can be eliminated if you have wireless. So you don't have to wire everything. Obviously, it's not that reliable as a wired system, but it can still work for some applications. Sedona, it's a very peculiar thing. It's basically the open source version of Tridium, JACE, that you saw before. Not super popular, but it's the first attempt of open source in this sector, 2008. From 2010 to now, a lot of companies proposed to build analytics. So fault detection and diagnostic, meter, billing, utilities that can help you to build different customers, to keep record of who spent what, to do meter analysis, etc. And this is SkySpark, which is an example, and you'll see it in the hands-on experiment. And Haystack. And both data analytics and Haystack are something that Gabe is going to describe in a bit in terms of way to code differently. So one of the big issues that we are all familiar with if you deal with building is each building is different. And each control system is programmed differently by a technician who you don't know how created the coding scheme, the naming scheme. So one is, one building has supplier temperature, SAT, discharger temperature, and 15 other names. So if you want to generalize and write your control code, it's almost impossible. So you have to go on each building, code everything manually, and Haystack is the first attempt of trying to abstract a little bit. So you can, for example, having graphics that they automatically instantiate. So you have all the points that are called in the same way, and they can be referenced. And an air handling unit A and an air handling unit B are not identical, but have enough in common, so a system can deduce what the supply and the return are and populate the graphic, which is a lot of hours saved, lower cost for users, and lower cost for companies in general, because technicians go out and they cost $200 an hour, and it's not fun for the owner. This is the funny piece. It took me a while to compile this. This is the last 20 years in building automation system with 4 or 5 relevant events. And these are the parallel in IT. So you go from your 50K modem, wow, that one, Windows 95, and your GPS. And then in the meanwhile, we had Amazon Web Service, which is the first cloud computing, Xbox, iPod, yeah, that was the name of it. Laptops, iPhone #1, Tesla. This is the first IoT device for homes, the Nest thermostat, which is smart, which is built on a Linux machine, which is now $300. iPads, Fitbits, Alexa, you can talk to this and we'll tell your kids to go and study. You have virtual reality. You have self-driving cars. And so the comparison is kind of embarrassing. This is an interesting one, and we'll see this again. These are hobby microcontrollers and microcomputers, which have a significant impact. So the question that, this is a quote from a guy who works with me. I'm not going to say who he is, but if an AI can drive my car following my voice commands, why is my smart building so dumb? The fact is that there's been a divergence from 2000 from what the building automation industry has done, which is very little, mostly because the market didn't really push them, and the IT, consumer electronics, and even electric cars industry, which had a lot of innovation. And the reason why your building is so dumb is because of that. So new buildings and new building automation systems are now asked to do a lot of things. So Marianne presented the grid perspective. So demand response. You have to follow renewables to avoid the duck curve. You have to be dynamic in your operation. You have to be good with occupants. You have to save carbon emissions and energy and water and everything. And the question is, can we do that with modern building automation systems? Well, the main barriers, and I'm getting to the end of my presentations, are the market is not really pushing. So there's really few players, maybe 5 or 6 major building automation system manufacturers who have like maybe 80-90% of the market, and a few minor ones. There's low competition, low innovation, and high costs. Pretty bad. There's legacy systems there, which we know they're there for 40 years, and you have still pneumatics in one of our buildings. And this whole technology is not interoperable. It's been there forever. If you have a microcontroller, it typically has low performance and limited functionality. So can you have your Alexa with your old Nokia phone from 1998? Probably not. And so you're in this situation in which there's artificial intelligence and other software stuff that are there and they're available, and IT people want to apply it to buildings, but then when you go down to the physical infrastructure, it's so old and decrepit that it can't quite keep up. building orders are locked in. This was the old strategy for, still kind of, I'm going to say old strategy for manufacturers, where you buy my X vendor and you're locked in with me forever. Now with BANCnet, this is slightly better, but still an issue. New systems are very expensive for both for hardware and software. They're not completely interoperable at 100%. The software is outdated, and the programming is painful. What?
Other than that,
We're good. So a few pictures, and I'm basically done. This is thanks to Chris. Some of the, this is a handmade board with things that somebody who's still running. It was running a year ago or something.
I just took that out of one of our servers last year. One of our servers that was running on literally one of our most important buildings in the entire campus.
So you got
Handmade wire-wound alarm processor that would send out alarm signals to the different trade workshops.
Where you have to get it out of, which is impossible to. There's 99 reheat zones, 70% failure rate. Other wonderful things, how you get the schedule out of the building. You print the graphic on a dot machine, and then you measure with a tape. This is, I'm getting to the end. This is why I think the new microcomputers coming from the hobby, the IT world, are relevant in this discussion. This is a Tritium Jace, which is the top of the most awesome thing. It runs a Java virtual machine, everything I described before. It's the gateway that talks to everything, like the Sorrow Ring. And it costs, though, quite a bit just for the hardware. Then you have installation licenses and stuff. This is a Raspberry Pi 3, $3,000 to $50. And if you look at the details, I'm not going to go through them. 1 gigabyte of RAM, it's the same. So that's what mass production does, and that's what we're paying for our systems. Obviously, it doesn't have input and outputs. It doesn't have a box. It doesn't have software. It's not perfect, but we're talking about something that the industry will feel very soon, competition from this type of products. This is the end. In this sad presentation, there's a hope for the future. Sedona is an open source Tritium machine, basically. These are the electronic microcomputers with an external board. So this and this makes basically the same function of that one. There's an article from a couple of years ago by a guy who's been in the BAS industry for years, and his kid was playing with microcontrollers. At 6th grade, he was programming them in Python. And he said, well, these guys are going to be freshmen here, and they're going to enter college and be out of the market. So in 20, no, what is that? The 8 years? No, what is that now? Yeah, in a few years from now, we're going to have people who are able to code and can enter the industry and can really revolutionize the way you do things.
They'll go work for Amazon.
And that's a challenge, but you see the stock market, so I don't know, maybe not. So this is important, I think, since you guys are training the new generation of people who are going to be technicians, and the industry is changing. What is going to look like in 10 years or 20 years from now, the skill set for a technician. These are interesting things. You're going to hear this from Gabe in a few minutes. But what I'm saying is there's more and more open source tools that you can use. And, time series database, they are free. It's just a different universe. In the last 5 years, this has been a revolution, and I think that this is going to impact the industry because they have to do something before. Yeah. Thank you. Yep.
I just want to say, I noticed people taking pictures of these. It's totally fine. You're also going to get a copy of these slides. So
What drove the development of Sedona?
So this is my personal take. There's a few people in this industry who have been very innovative. The same people who made Tritium and made Sedona after leaving Tritium then created SkySpark. And it's basically a bunch of people who are more like IT oriented, and they think more like IT people. And so I think their business model changed, and they went from building Tritium to building analytics, and they want to have a hardware component that they could, say, you can buy this and use our analytics on top of it. So I think that was, but that's my